Welcome back. In this video, we are going to start chapter 2 on differentiable maps. So this chapter will contain 3 sections: Section 2.1 Definitions and Fundamental Examples, Section 2.2 Rules of Differentiation, and Section 2.3 about functions of several variables and functions with several components. Okay. So the first section is a little bit lengthy, so I will split it into 3 videos. So in this video, I'm just going to give the definition along with some motivation and some basic results, okay? And in the next video, I will give the fundamental examples, and in the third video, I will give the differentiability of the inverse function. Okay. So, but before we start, let us recall some very convenient notation, the big O and small o notation that you probably encountered. But I'll give a little bit, I'll do some generalization of them. So instead of working in R, we can work in any normed space. So suppose that we have 3 normed spaces, E, F, G, and we have U, a subset of E, and a point A in U. And if you are working in R, or if U is an interval, for example, which is unbounded from above, we can take A to be plus infinity. You will see why. What do I mean by that? But in most of this course, we'll just work around 0, around the origin. Okay, so if you have 2 functions now, small f, from the subset U of E into f, and another function from the same subset U into the other normal space G, we say that f is a small o of G, or f of x is a small o of G of x near x equal a, or as x tends to a. This is just a shorthand notation for this condition. The condition that tells me that the norm of f over the norm of G tends to 0 when x tends to a. Okay? And of course, you can write this with the epsilon delta notation. So saying that this tends to 0, it means that it can be made less than any number epsilon positive, provided x is sufficiently close to a. So I can write this in this way. Okay? For every epsilon positive, we can find some number delta such that if the distance between x and a is less than delta, then the norm of f of x is less than epsilon times the norm of g of x. Okay. And big O notation, we say that f of x is a big O of g of x as x tends to a, or near x equal a, if there is a constant, so independent on x, such that the norm of f of x is less than the constant c times the norm of g of x. So the ratio is bounded, if you like. So small o means that the ratio tends to 0. Big O means that the ratio is bounded. So they are very, very useful notation in asymptotic analysis. Now, for example, if you work near x equals 0, then you know that len of 1 plus x is a big O of x, because we can write the power series expansion. So it starts with x, and then minus x squared over 2, and so on. So we say that it's of order of x. Okay? Or if you like, len of 1 plus x over x is bounded by some constant. Sine x can be written as x plus big O of x cubed near 0, because this is the Taylor series of sine. So you can think of this as higher terms, higher order terms, if you like. Now, near infinity, len of x is a small o of x. Why? Because len of x over x tends to 0 as x tends to infinity. Okay. Now, I use this small, maybe you didn't encounter this in this generality, but for example, if you are working in a normal space, instead of writing that f of h is a small o of the norm of h, we can simply write f of h is a small o of h. So this simplifies a little bit the definition, but it's exactly the same thing. This means that norm of f of h over norm of h tends to 0. Okay, the norm on R is just the absolute value. So absolute value of the norm is just the norm. So this is just a shortcut for this, which is a shortcut for saying that norm of f of h over norm of h tends to 0. Okay, so this simplifies a little bit. Now, some important rules. For if you are working with a real variable x near 0, then saying that f is a big O of x squared implies that f is a small O of x. Why? This is because this means that f of x is less than a constant times x squared. So when I divide by x, an absolute value, I get less than cx, and this tends to 0. So a big O of x squared is a small O of x. But of course, the converse is not true. The second rule is that we can add, so small O of x plus small O of x is small O of x, and same thing for minus. Minus small O of x is also small O of x. Let's go back to the definition. So this is not really a number. Okay, this is just a notation, a symbol. Okay, you can think of it as being a set, if you like. It's the set of functions satisfying the condition. And if I multiply 2ox, small o of x by themselves, I get small o of x squared. Straightforward. Okay. And big O of x plus big O of x is big O of x minus same thing. And big O of x times big O of x is big O of x squared. Okay, so these are really straightforward to check. And they are very convenient because they can simplify lengthy computations, actually. Okay, so having said this, now we move to the definition of differentiability of a map. But before doing that, let us revisit the notion of differentiation of differentiability of a map from a subset of R into R. Okay, because we'll try to bring out a condition that can be extended to the general case of normed spaces. Okay. So what do we mean? What do we mean by saying that f as a function of one real variable into R is differentiable or has a derivative at a point x? We usually assume that the domain of I is open. I will tell you why in a moment. Why would you need this assumption always? So consider a point A in the domain of f. We say that f is differentiable at A if this ratio, f of a plus h minus f of a divided by h, has a limit as h tends to 0. Okay? So it means that in particular the limit exists, it's a real number in this case. And this limit is denoted by f prime of a or df over dx at x equal a. And as you know, it's called the derivative of f at a, and it has a beautiful geometric interpretation. It's the slope of the tangent to the graph of f at the point a, f of a. Okay, now we say that f is differentiable on its domain if it's differentiable at every point of the domain. Okay, so first we define the derivative at the point, or differentiability at the point, and then we define differentiability along the whole domain. And now, why do we need that the condition that I is open? That because if you look carefully, this ratio, in order for this ratio to exist, we need to ensure that a plus h is in the domain of f. Okay, so we need this condition. If for every a in the domain and for every h sufficiently small, a plus h should belong also to the domain in order for this to make sense. And if this is true for every a, then this means that this is precisely the condition of openness. Okay? Condition of openness means that whenever we have a point in the set, all points sufficiently close to that point will also be in that set. Okay, so this is why we usually define the notion of differentiability on an open set. We need the condition of openness because we want to ensure that this ratio is well defined, at least for h small enough. So this is the first remark. Now, okay, we cannot generalize this definition directly to maps between normed spaces because we cannot divide by a vector. Okay, so vector over a vector is not defined. So we need to transform this condition a little bit to make it generalizable to our more general context. Okay, so let us do that. Okay, f is differentiable at a. We can write this condition as saying that the limit of this is by the way called Newton ratio. Okay, so this means that Newton's ratio minus L tends to 0, minus the limit. Okay, here I should say, yeah, so L is the derivative of f at a. Okay, if I reduce to the same denominator, I get f of a plus h minus f of a minus LH over h tends to 0. And this precisely means, according to our convention, that I can write the numerator as small o of the denominator because the ratio tends to 0. Or if you like, f of a plus h is f of a plus LH plus a small term of zeros. Okay, so plus small o of h. Now, or if you like, if you go back to the definition, for every epsilon positive, we can find a number delta such that if h is sufficiently small, is less than delta, then the difference between f of a plus h and f of a plus LH is less than epsilon h. So all these precisely mean the same thing. But now we advance a little bit because now the geometric condition 4, 5, 6 have the same geometric interpretation, which is that locally near A, the graph of f, because if you look at this term, fa plus LH, this is what? This is the equation of the tangent. So this formulation, this or this or this, same thing, tell me that when f is differentiable, the graph of f looks locally like its tangent. It can be approximated by its tangent. Okay? So this is the idea of differentiation. It's basically it's linear approximation of a function locally. Okay? Because the graph of f may be not linear, but its tangent is always a line. So this is now, it turns out that this is really generalizable. And the first idea is that instead of, if you look at the term LH, we can, okay, how to generalize the notion of product of two numbers? If you have a Hilbert space or an inner product space, okay, we can just replace this by the inner product between two vectors L and H. But we can do better actually. We don't need just to work between inner product space. We can work in any norm space. The term LH, which is the linear term approximating the function locally, is actually, as a function of h, is linear and of course continuous. So this is the idea now. Okay? So now we are led to this definition. So we have two normal spaces E and F, and U an open subset of E, okay, and a point A in U, and you have a map from U to F. Okay, so the map need not be defined on the whole space, but it's defined on an open subset of the space. Okay, so we say that F is differentiable in the sense of Frechet or Frechet differentiable at the point A if there is a linear bounded map from E to F such that F can be approximated by this linear map or by this affine map, if you like. So near H equals 0, f of a plus h minus f of a minus this linear term is small o of h. So if you like, we can put the norms because these two conditions just mean the same thing. Okay, this is just a shorthand for this. Or if you like, the ratio tends to 0. Or if you like, you don't like h, you can replace a plus h by x. And then this condition of differentiability at the point A is the same thing. So it's just f of x equal f of a plus this linear term plus small order terms. Okay, so this is, now I have several remarks before we continue. You can also still write this in other ways. So instead, if you don't like the small o notation, you can write it as remainder times norm of h, where the remainder tends to 0. So it's precisely the same thing. Just put the remainder to be this difference divided by the norm of h. Okay, so you can, so the remainder you can write it as small o of h, small o of norm of h, r of h times norm of h, or if you like, epsilon of h, where epsilon of h satisfies this condition. So you use the notation that you like, but they all mean the same thing. Okay? Or you can go back to this definition with epsilon and delta. Okay, so the idea is the same. It's just linear approximation. So there's no mystery. Now, we will see that if this condition holds, then the operator L, the linear bounded operator L, is unique. It's not difficult to, we'll prove that. Okay? And it is called the Frechet derivative or Frechet differential of f at the point A. So this is the point A, not x. Okay? Now, why I'm saying Frechet? Because there is another notion of differentiability, a weaker form called the Gateau differentiability. But it's not part of your program. So I will talk about it a little bit by the end of this chapter, just for curiosity. But in this course, we'll be just focusing on the Frechet differentiability and Frechet derivative. Now, derivative, differential, same thing. So we'll just talk about the derivative or the differential. Okay. So derivative, differential, same thing. It's a linear bounded map. Okay. And this derivative is denoted by one of these symbols, f prime of a, df of a, df sub a, or df at a, small d or big D. Okay, so you can see, you can encounter all these notation actually. You choose the one you like. And as I said, there is a weaker form of differentiability called Gateau differentiability. Now, Frechet and Gateau were both French mathematicians who worked on this notion of differentiability. And yeah. So in this course, we'll just say differential, okay? Now, why the operator L is unique? To prove this, we need a lemma. If I have a linear map between normal spaces S, and near 0, S of H is a small o of H, meaning that norm of S of H over norm of H tends to 0, then necessarily S is the 0 operator. So of course it's continuous. Okay, good. So let us prove the lemma first. Okay, let epsilon be a positive arbitrary given number. Now, this condition precisely means that you can find delta such that norm of S of H is less than epsilon norm of H, or the ratio is less than epsilon, same thing, provided norm of H is small enough, less than delta. Okay, and now take an arbitrary element in Ex, which is non-zero, and consider H to be delta over norm of X times X, so it's a multiple of the vector X. Then the norm of H is precisely delta, so it's less or equal than delta, and therefore, according to this condition, L of H is less than epsilon norm of H, which is delta. Okay, if you go back to the definition, this means that a norm, yeah, this should be S, not L. Okay, so because you put this L, so this is just S. Okay, so S of delta over norm of X times X is less than epsilon delta. Now, since S is linear, I can put the scalar outside S, and then this is the homogeneity of S. And then I can put outside the norm. So I get delta over norm of X times norm of Sx less than epsilon delta. And so when I simplify by delta and multiply by norm of X, we did this before, we get norm of Sx is less than epsilon norm of X. And of course, here we assumed X is 0, but if X is 0, it's true because you get 0, 0. And therefore, this is true for every X. And as you know, this implies that S is bounded and its norm is less than epsilon. But epsilon was arbitrary. So the norm of S equals 0, and therefore S is 0. So please correct that. This is SH, not LH. Okay. So this proves the lemma. And now it's easy to prove proposition 2.1. Suppose that we have another bounded linear operator T satisfying this approximation property. And L is the derivative actually at A. So we have these two identities. If we subtract them and use the rules of small o of h, these two terms cancel. So you just get T minus LH is a small o of h. So it's just small o of h minus small o of h. So it's small o of h. And by the lemma, T minus L is the zero operator, and therefore T equal L. Okay? Now, last remark before we stop this video. If we specialize in the case E equal F equal R, the derivative by definition, by our general definition, is just an element in L of R and R, which is the set of linear maps between R and R, and they are automatically bounded. And we know that we can identify this with the R. So the derivative at A can be identified with a number, and we get our usual familiar definition of the derivative. Okay? So if you do this identification, our definition, the calculus definition of the derivative that you know from first year or from high school, is a particular case of Frechet differentiability in the context of norm spaces. Okay? But we have to just do this small identification between linear maps from R to R and numbers. Okay, we talked about that. Okay, and now differentiability on a domain, as you expect, means differentiability at every point of the domain. Okay, so if F is differentiable at every point of the domain U, here one more time, you need the fact that U is open. You understand why? Because the definition we need that F of A plus H is in the domain of F for H small. And if F is differentiable on its domain, then we get a new function now. But look, the domain is U, still the same. Okay, it's where X varies. But the range is not F, it's the set of linear bounded maps from E to F. Because when I put here A, then F prime of A is really an element here. Okay, so we get a new function, and now we have a topology here and you have a topology here. So this is a subset of a norm space, and this is a norm space. So it makes sense to talk about the continuity of this operator, F prime, which is usually non-linear. Okay, so the range is linear, but F prime. Okay, and so if this function is continuous, we say that F is of class C1, or that F is continuously differentiable. And important remark, because we have two kinds of continuity now. In the definition of the derivative, we said that the derivative is continuous, is linear bounded. And here we are talking about continuity of F prime. So it's not the same thing. As an operator, so if you look, so F prime of X is, when it exists, is by definition continuous. But f prime as the function from u to L, E, and f need not be continuous. Okay? So, in simpler terms, if you consider the term f prime xh or dfxh, it's a function of two variables actually. It's a function of x and a function of h. So the definition tells us that as a function of h for fixed x, as a function, this is continuous in h. Okay? But continuity of the derivative, so as a function of x, it's not necessarily continuous. Okay, and you already can give examples in one dimension function that are differentiable but are not. No, I'll give an example, but are not. So we can find a function, a differentiable function which is not C1. Okay, so here's the last example. Take f from R to R, just to be x squared sine 1 over x if x is different from 0, and 0 if x is 0. Of course, you can easily check that f is continuous because this is a bounded term. So when x tends to 0, it tends to 0. Okay. Now, actually, f is more than continuous. It is differentiable. Now, why is it? How do I prove that? It's differentiable at every point which is not 0, because it's a product of two differentiable maps, so the usual rules. And it's differentiable at 0, so we have to just be careful about 0. So go back to the definition. If you look at the ratio f of h minus f of 0 over h, f of 0 is 0, so you just get h squared sine 1 over h. So it's just h sine 1 over h, and this has a limit. So the existence of this limit implies that f is differentiable at 0 and its derivative is 0. Okay. Therefore, f is differentiable everywhere, but it's not C1 because the derivative. So the derivative at 0 is 0, we know that. And if x is not 0, just can differentiate this expression. So it's a product, so it's 2x sine 1 over x plus x squared times the derivative of sine 1 over x, which is cosine, times the derivative of 1 over x, which is minus 1 over x squared. And therefore we get this expression. And we see here that f prime is not continuous. Okay, so this is an example, fundamental example of a differentiable function which is not C1. Okay, so okay, and I think I will stop here. And in the next video, I will give some fundamental examples of differentiability and non-differentiability. So thank you for your attention and see you next time.